self-organizing map. And the talk will be delivered by Professor Dr. Tondrapal from NIT, National Institute of Technology, Durgapur. So first, I wishes to convey my heartiest thanks to Professor Dr. Tondrapal for accepting our invitation. So thank you, madam, and welcome you, madam, in the program.
Thank you, Professor Shankar. Thank you so much, especially the organizer, to give me the chance to share my knowledge to the young faculty members, research scholars, and the students.
Okay. So before going to the main session, I just wish to tell the profile of Professor Dr. Tondrapal. Dr. Tondrapal is a professor in the Department of Computer Science and Engineering, National Institute of Technology, Durgapur, India. She received the BSc degree honors in physics and BTech degree in computer science and technology from Calcutta University, Kolkata, and ME degree in computer science and engineering and the PhD degree in engineering from Jadavpur University, Kolkata. Since 1994, she has been with the Department of Computer Science and Engineering, National Institute of Technology, Durgapur, and acted as the head of the department during 2007 to 2009 and January 2019 to March 2021. Her research interest includes soft computing, multi-objective optimization, fuzzy logic, fuzzy decision making, artificial neural networks, machine learning, and pattern classification. She has about 70 publications, including books, book chapters, conference papers, and 40 journal papers. She is associated with 4 projects sponsored by MEITY and DST. Currently, she is the chairman of IEEE CIS Kolkata chapter. I again wishes to convey my heartiest thanks to Madam for joining this event. Thank you, Madam, and over to you, Madam.
Thank you again for your nice words about me. Okay. Uh, as my lecture is basically on self-organizing map, which is a neural network, and I would like to give emphasis on useful properties, especially clustering by song. So to recapitulate, actually, what is clustering, and there is a basic and simple clustering algorithm called K-means clustering. I will just give a brief description and demonstration on K-means clustering, such that the clustering of sum can be compared with this clustering scheme. Okay, then let us start it. And I would like to request all the participants to put any questions, even while I will be discussing on the topic. Because if it is not clear to you, then it will be difficult to follow the next discussion. I'll be very much pleased if I can can clarify your questions and doubts. So please, you interrupt my discussion if necessary for any clarification of my topic. So let us first go to the K-means cluster. Is it visible?
Yes, madam, it is visible.
Okay. Now I'm
Yes,
going
madam,
to
if you can make it full view.
Slide show from beginning. Yeah. I forgot to
Yes, ma'am.
put
Please.
my name and the name of my institute and email ID. I think the organizer will share you my email ID and my mobile number. Also, it is in our website, on the website of NIT Durgapur. You will get everything. So, K means clustering. It is the process. What is clustering? The process of grouping a set of objects into classes of similar objects, or maybe based on dissimilar objects. That is, if they are similar, then they will be included in the same cluster, and if they are not similar, that is dissimilar, then they will be included into different cluster. Okay, so in this case, cluster means a group having similar objects. And clustering is basically unsupervised algorithm or learning, unsupervised learning. Why it is unsupervised? Unsupervised means there is no supervision. Actually, physically, there is no question of teacher or supervisor. However, presence of supervisor means the target. That is, what is the output, ideal output or ideal class in case of classification, right? That will be given. But in unsupervised, there is no such information about the target of the samples. And clustering belong to unsupervised learning. And one thing I'd like to mention is that classification is always supervised. However, clustering can also be used for classification. That does not mean that in that case clustering is supervised. Actually, the clustering we can use for grouping, and sometimes we use this group initially for the classes. Different classes are actually, we consider different clusters, we consider it as different classes. Here we see that all the small circles, these represent uh, samples, or so actually that a data set consists a set of samples. Now in this case, here it shows the input samples in the input space, and here actually for the sake of simplicity always we have considered the two-dimensional, because we can see the two-dimension in well, then three-dimension, and if it is more than three-dimension, then it is very difficult to visualize it. Then we have to consider different methods for visualizing the distribution of the data set. And that is the importance of SOM, that is multidimensional input space will be mapped to the out space where the dimension is less, such that we can visualize it properly. However, now forget the SOM, let us go for clustering. And in this case, we have actually intentionally we have considered the sample such that there are three groups. And for example, for here for three different groups or cluster, we have considered three classes. So all the samples colored blue belong to one cluster, and all the samples colored red belong to another cluster, and all the samples colored green belong to the third cluster. So total three clusters are there. So in this case, for sake of simplicity, we have considered only two-dimensional input space. So in this case, here the small circle, we can consider it is a point in the two-dimensional space, or maybe X and Y coordinate. Now, in K-means clustering, there is one disadvantage, that is the number of clusters is not given. So before we start the k-means clustering, we have to assume the number of clusters. Number of clusters may be 2, maybe 3, maybe 4, maybe 5. Then there may be one question that how we will know this is the optimal number of clusters. Actually, there are so many techniques for determining the optimal number of clusters. There are some indices. I am not going to that cluster indices. Here we will assume that we know the number of clusters, and based on that we will actually explain k-means clustering. And it is a very well-known clustering algorithms due to its simplicity and widely used in many applications. As it is very simple, that's why I am discussing k-means in brief, such that you can remember about k-means clustering, its principle, and you can compare it with the clustering of sort. Here, each cluster is represented by the center of the cluster and the, just a minute, hello, Dr. Shankar.
Yes, madam.
I can see some parts of my screen due to this. How I can, just a minute, how
Prem
I
Kumar, are you online? Prem Kumar?
hide this our symbols actually.
We can see the entire screen, madam. We can see the entire screen.
But I can't see.
Yeah,
okay,
Prem Kumar, can you please help?
Okay, I have shifted it. I have shifted it. And also, I think we can also shift. Can I take it below the taskbar? Because
Ma'am?
some of
Ma'am,
the
screen is visible. Screen is visible. You may continue, ma'am.
you can see it, but I can't see the whole screen. The
In
taskbar
that case,
menu.
you can double click on the center position. Double click on the center of the screen.
No, it is not going.
So, ma'am, in that
In
case, you
Google
can
Meet, there is an option
pin.
hide, but it is not there.
You can, ma'am, drag it.
I am trying, but if I drag it, then yeah, still, but if I can't take it to the bottom, I can take it to
Ma'am, from our end, everything is visible.
okay. It will not be very difficult. Okay. So a center is actually identified by its a cluster is actually identified by its center. So the result of clustering algorithm is nothing but the centers. How many centers? As many number of clusters. Now in k-means clustering, there are some assumptions. First, I have mentioned that number of clusters we will assume we know it, and all the clusters are disjoint. That is, there is no single data which belong to more than one class. But in real life, some samples may belong to more than one class. That is actually the limitation of k-means clustering, and there are some other limitations also. I am not going into the deep detail of it, as we are not interested in actually in k-means cluster. In k-means clustering, there are two main steps. What is this? Initially, we have to randomly select the centers. For example, there are 100 samples, and we know there are 3 clusters. We are assuming that there are 3 clusters. So randomly, we will consider 3 points as 3 cluster centers. Our objective is actually, or our aim is to change this cluster step by step, that is with time or with iteration, and ultimately they will be stable in the final position. So initialize with k random points from the input space, or we can also consider for k data or k samples from the data set, input data set. Now, corresponding to these points, we will take all the data points one by one, and we will assign to one of the cluster which is closest to it. That is, say there are 100 samples and 3 clusters. So there are 3 centers, say C1, C2, C3. Now from all the data points from 1 to 100, say we are taking the data point 1, then we will measure the distance from this data point to all the cluster centers, and we will assign that data point to that cluster for which the distance is least. Okay. So in this way, all the samples will be actually labeled in which cluster it is according to the current cluster center. And next step is to modify the cluster center. That is, then we will consider for a specific cluster, we will consider only those samples which belong to that cluster, and we will take the mean of them, and the new cluster will be the mean of those points. I will demonstrate it, then I think you will understand it more. Now, what is the objective function of k-means cluster? For any cluster, actually, you will see there are 2 concepts. One is intra-cluster distance and another is inter-cluster distance. I am now going back. For example, for these 3 clusters, we always try to make any cluster as compact as possible. That is, the samples will be very close to each other. This is called intra-cluster distance. So always we want to minimize the inter-cluster distance. And what is inter-cluster distance? The distance between 2 different clusters. That is the distance between the center of this cluster from the center of this cluster, or from the center of this cluster, will be as far as possible. Okay. So here you will see for any clustering algorithm, we try either to minimize the inter-cluster distance and maximize the inter-cluster distance. Now here you see what is objective function actually representing. Now in this case we are considering their total number.
Excuse me, ma'am.
Yeah.
Ma'am, the slide is stuck at introduction. So,
Hello.
ma'am, if possible, please reshare your screen because the slide in at the introduction page only.
Really?
Yes, ma'am. Please reshare it, ma'am. Stop the sharing and please
Okay.
reshare it.
Thank you. Just a minute. I would like to go to my slides. One slide is there.
Ma'am, are you sharing the screen?
Yeah.
Yes, ma'am.
Now can you see my
Yes,
slide?
yes, ma'am. Yes, ma'am. Yes, ma'am. Objective function.
Yeah. So here already we have mentioned that the clusters are disjoint. So here let us consider there are k such clusters and total number of samples is m. Now for xi means ith data point and mu k is the center of kth cluster. Now here what we are assuming when we are measuring the distance from the data to the cluster center, the ith data, the difference or distance from the ith data to the kth cluster. If the ith data belong to the kth cluster, then only wik, that is, will be 1. So in this case, you see, when we will compute j, then we are considering the summation of those points here. So it will give the average distance of the points or that total distances of the points belonging to that cluster in which it belongs. Similarly, it will be done for all clusters. So you see, in this case, we are actually considering only the intra-cluster distance. Have you got it? That is, this distance we will consider when omega ik equal to 1, and omega ik will be 1 if I belongs to the cluster K. If I does not belong to the cluster K, then omega ik will be 0. So when we are computing this expression, which is actually basically the distance, then you see only the inter-cluster distance of all the clusters will be summed. So in K-means clustering, actually we are trying to minimize this objective function which represents the intra-cluster distance. So this is the minimization problem. Is it clear? Hello, participant? I don't know
Yes,
where, maybe they are muted.
yes,
Sir,
yes.
objective, ma'am, objective function. K means algorithm. Yes, ma'am.
Yeah. So here again, the K-means algorithm, that two steps or phases, it is elaborated by this expression. So there are k random data points initially. Then these 2 and 3 will be repeated. That is, we will assign each data point xj to the closest centroid. So from xj, the distance of all the cluster center will be computed, and for which it is less, the j will belong to that cluster. Then we will consider the cluster one by one. That is, if we consider a particular cluster, then all the points will be considered and their mean will be taken as the new center. In this way, the center will be modified for each iteration. So these 2 and 3 will be iterated or repeated in different iteration. And when we will see the cluster centers are not being changed, then only we will stop. That is, then we will assume that it has converged. And that is the final centroids. And already we know that centers are the results of any clustering algorithm, because once we get the center, always we have the data set, so we can easily find in which cluster a data set belongs. Now, just I would like to demonstrate it. Here you see all the small circles, or you can consider it as a point in a two-dimensional space, say XY coordinate, right? So in this case, it shows the positions in the XY coordinate, the position of the points. Now, all the points or small circles actually shown by the green color. this is the initial data set, and we don't know in which cluster which points belongs to which cluster. Okay, that's why a single color has been used to represent all the samples or data. Now here we are assuming that two clusters are there. We can consider three clusters also, we can consider four clusters, but for demonstration purpose we are considering that there are two clusters, and we have randomly from the input space we have selected 2 points, which is given by this cross, so red and blue. So we are assuming that these are the currently centers of the cluster, initial centers, and the cluster which belong to this center will be colored red, and the cluster and the points which belong to this cluster will be colored blue. So now you see the initialization of the centers is complete. Now we have to go to the phase 1. So you take the points one by one, say this point. Now you see the distance of this point, that is the data from the center of this cluster is less than the center of this. So now what we will consider, this sample belongs to this cluster. So now you will make it red. Now we will take one by one all the samples, and accordingly we will color it according to its corresponding cluster. Now let us consider, say, this point. For this point, actually the point means data. Data means that is a single data, and it is also sample. We actually use different words, different name for different purpose. Now for this sample, you see the distance is less from this cluster center, so this sample will be colored blue, and accordingly you see this is the result. So you see after first phase, that is for categorization of the samples to its cluster, assigning the samples to its cluster is done. Okay, now the second stage. In the second stage, what we will do? The change of cluster center or updation of center. Now, what will be the new center? The new center will be the average of all the samples of red color, and that will be the new center of this current red color center. Similarly, we will take the average of all these points, and that will be the new cluster for the green cluster. And you see here, this is the, you see, I think you can remember their shape, okay, and sorry, the shape, and you see it will be actually the mean or average of this. So it will come, I think, here, and for this it will come here. Okay, so you see that happens. But these are still, you see, this belongs to this cluster, and all these samples belong to this cluster. Now, what is the next step? Just we will repeat it. Again, you will see some points which are red, that, for example, some points say these points red. Okay, these sample you see now, after the updation of the center, these points become more close to this blue center than the red center. So with respect to this new cluster, now you see these actually belong to this cluster, but not this cluster. Okay, so in this way we will consider all the samples again, and again we will assign to the corresponding cluster, and you see this is the change. Okay, the color, you see this red has been colored blue, as the blue center is closer than this center. Now again you see the center are not yet changed. Now the center, the average of this will be the new center, and you can just guess that it will be shifted here because more points are here. And similarly, it will be shifted little bit here as more points are here. So in this way, you see, this has been shifted here and this has been shifted here. So this is now currently the average or mean of all the blue points, and this is currently the average mean of these blue points. Okay. Now in this way, again, we will repeat the process, and ultimately you see this will be the final cluster center. Now if we reassign the the samples, you will see there will be no change. So there will be no change of the cluster center. Okay. So this is the claim is clustering, and it just shows that how the centers are being updated from the initial random points to the final position and the corresponding change of colors of the samples. And you see, yeah.
I have a question, ma'am. In the K-means algorithm, you were telling us. So you have told that the first after the initial centroid, we have to for each data point we have to choose the closest centroid. So ma'am, I can't understand it. Will you please explain it twice?
Okay, just a minute. That is the main thing here. You see, okay, just here, this is the samples, all the samples, right? Now, this is the input space. From the input space, we can take any 2 points as the initial center. That is the random points. Actually, these will be changed with iteration. This is a learning algorithm, right? So the center will be learned one by one according to the algorithm, and the algorithm, the principle is to make the intercluster distance less. Okay. So here you can consider any point from the input space, or you can also consider any samples, that is input data, which are provided for clustering. For example, say even you can take these two as the initial centers, or you can consider these two, or you can consider one here, you can consider, you take any two points as the two initial cluster. But following the algorithm, ultimately this cluster will be modified for in each iteration, and ultimately when it will go to the final point, then you will see after that there is no change in the in assigning the data to the clusters, and so no change in the results. Is it clear or not?
Yes, ma'am. Thank
However,
you.
there are some advantages. That is, if there is any outlier, outlier is basically you consider as a noise which is for apart from the samples. That is called outlier. And also for initialization, different initialization, there may be some problems that I am not going. Okay. If you go to any literature, you will get it. So you see, in this case, the initial points we have taken, it is shown from which it is being shifted. So initially, one cluster point was there and another cluster here, it was there. But you see, ultimately it shifted. Now, initially, you can take the point here, right? And another point here. Then also, ultimately, it will be shifted. But maybe the formation of the cluster may look in a different way. Now, this is an example of 3 clusters. Again, I would like to mention that here the disadvantage is we don't know how many clusters are there. So in this case, actually, there may be 4 clusters. For example, if we consider there are 4 clusters, maybe this will be one cluster, and this will be another cluster, this will be another cluster 3, and this will be another cluster. So according to our assumption of the number of cluster, actually the clustering will be formed accordingly. So in this case, you see, initially all the color is same because we don't know which point belongs to which cluster, but ultimately three different color have been used to denote three different clusters. One is violet, another is green, and another is red. Now this is only to show one cluster, that is what was the random points and how it ultimately moves to the final points. Okay, that is to show this. So this is, I think, the conceptually, and by little bit mathematics, I have tried to describe and demonstrate the working principle of K-means clustering. Now next we will go for the sum. Actually, there are many useful properties of sum that we will discuss, and at last we will discuss the clustering. So let us go to the next cluster. Next topic. So if you have any confusion or any query regarding K-means clustering, then I will try to explain it. I'm not an expert in clustering, frankly speaking, but I will try. Throughout our life, we are actually trying to improve our knowledge. Okay, just a minute.
Participant, please, if you have any question or doubt, please ask to ma'am.
Yeah.
I have a question, sir.
Yeah.
Okay, please ask to ma'am.
Yes.
Yeah.
Yes.
Madam, as excellent presentation, I have a question. Like you told the how we approach to a problem solving using K-means cluster. But suppose in a real life scenario, I'm facing a problem and I have to do the cluster analysis.
Yes.
Is there any unique way so that where we can determine, okay, this may be the best way of solving this problem using cluster analysis,
This
or
is very,
we have to go by trial and error?
yeah, this is very, very common question, however, very, very difficult to answer. There is no algorithm in the world which is suitable for all types of problems, maybe cluster.
Exactly.
So you see, there is not only K-means clustering, there are different types of clustering algorithm. For example, hierarchical clustering. This is one of partitioning clustering, right? There are hierarchical clustering. In hierarchical clustering, there are two categories. One is bottom up, one is top up. One is called decisive, another is called agglomerative, right? There are some other partitioning clustering except K-means, and in K-means you see there is an ideal assumption that one cluster will belong to only one point, or one sample will belong to only one cluster, but this is not realistic. For example, there are two clusters, one belong to the singer and another belong to the dancer, but a particular person may know both of them. Okay, so there may be overlap in practical situation. The cluster is overlapping. So in that case, we need the K-means algorithm has been changed to fuzzy Siemens algorithm, in which a particular point or sample may belong to more than one cluster. So you see, there are so many algorithms, and we can claim this algorithm is suitable for this type of application. When we, for a given application, when we consider to apply some clustering algorithm, then we see the literature, and we try to understand which algorithm will be suitable for it. Accordingly, we do it. And regarding the number of cluster in K-means clustering, there are so many indices. That is called clustering indices, right? So that is used.
That's what actually I was asking, madam. Like in say, just giving an example, say a problem we're trying to solve using logistic regression, right? There we have different value, like one value is adjusted R square. Okay. Now if we see there are two, I have done the exercise twice using.
Hello. Hello, you are not audible.
Not audible. Bothinda, you are not audible. I think the connection is problem. Madam, another question.
Yes.
One person asks, Dr. Rakesh, ma'am, many clustering is exist, but when we use k-means clustering?
This is also very interesting. Interesting. Though k-means clustering, there are so many limitations. However, still now, I have seen that many researchers are using k-means clustering for their problem, and it is giving more or less good results. But we can't say for all applications it will be give good performance. There is no such guideline. No one can.
I got your point. Sorry, I got disconnected in between. But yes, I got the answer. So in other cases also, we have to go like that. Like we'll do it one logistic regression and we're done. It's not go in that way. So maybe we have to try out the different combination of that.
Right.
Okay, madam, I got my answer.
That's
Thank you.
why there are so many classifiers for classification problem.
Right.
We use the regression, we use the decision tree, we use base classifier, net-based classifier. We can use SVM. No one can predict that for this problem, this data set, this classifier will be best.
No.
That is the research actually for different. We are always trying to find out.
No, my question is a little different. Yeah, I understand there are so many classifier rules.
Yeah.
But I was telling a different point. Like I have used two clustering methods. How do I know one is better than other? There must be some indices on that. Right. That's what you are telling.
Yeah.
Yes. Yeah. Thank you, madam.
Yes, there are so many indices. For example, base partitioning index, energy, and DB index. I cannot remember the full form for B and D, two scientists, and also PPM. You know, Professor Sanghamitra Bandyopadhyay, now director of ISI, he has devised actually three authors are there. Professor Maulana Pakhira, Sanghamitra Bandyopadhyay, and Ujjwal Maulik, and they have used they have given the name PBM, P for Pakhira, B for Bandyopadhyay, and M for Maulik, and it works very nice, this clustering index, and they have so many publications based on PBM clustering.
Oh, that I didn't know. That's really interesting. I'll explore those.
There is no unique solution, right? Thank you for your very nice, interesting question. So let us go for the next presentation. Is it visible now?
Yes, ma'am.
Yes.
Self-organizing map.
Yeah. Actually, still today I have modified a large portion of it. Self-organized map, organizing map. It is actually devised by Kohonen, I think in the year of 1980, most probably. And that's why it is called Kohonen's feature map. Kohonen's is a scientist name, and feature map is a very important term. Feature map, actually, what is learning in this case, in neural network, a self-organizing map is a neural network, but the conventional way the neural network learns, it is different. I will, of course, I'll go the detail of it. And it is self-organizing, means it does it work on its own. There is no such supervisor. That is, it is unsupervised learning. Now, very simple architecture you will see. Only two layers are there. One is the output layer, and these nodes are called the neurons, right? And this is the input layer, by which we profile the input samples or data or elements. Okay, so by this SOM, actually, this is nothing but a mapping which we call feature map from this input space to this output space. Okay, now let us go step by step into the detail of it. Hello, Dr. Shankar. What is the time remaining?
Time still is 45 minutes, madam.
Remaining. So 1 hour,
Yes.
15 minutes past.
Yes,
Oh,
yes.
sorry. Okay, these are the content. And already I have told, oh, so sorry. Yeah, 1918, by Conan, it was devised, and it is unsupervised learning. And the name self-organized actually indicates that it is unsupervised. Now, actually, the way we see the different things, different elements around us, actually, this is the mapping from that input to our cortex. Okay, so the similar mapping actually we use it, and this mapping from the element, for example, I can see the curtain in my window. This window actually is being mapped in my eyes. Okay, and it maintains the topology of the input order or input feature, and that's why topology means the inputs which are close together, that also in the output they will be close to each other. So in this case, that's why we see, for example, when I see a person, then I see that the eyebrows and the nose and my mouth, they are in neighbors of each other. However, the leg, never we see that our eye is in the bottom, near leg. So this is called the topology conservation. That is the input, the ordering of the feature in the input that will be preserved or maintained in the also the output space. I think it will be more clear with our discussion. Now, according to this motivation, actually, there are two layers. In the first slide, I have seen that the output is in the one-dimensional. But here I have shown that output is two-dimensional. Okay, so generally, the SOM is used for the better visualization of the high-dimensional data. When the dimension is very high, then actually it is very difficult to visualize. For example, if it is 4, 5, 6, and maybe 100 dimensions in our real life data, there are so many dimensions. That is the features of input samples, right? And we cannot even display it using our software tools. Okay, even if we display, this is not very easy to conclude or interpret. Okay, so always we try to map a multi or big dimension data to low dimension, and in most of the cases the output layer is used two-dimensional. So the multi-dimensional input data is converted or mapped to the feature space in the output by only two-dimensional. So here actually this is shown as the output space. Okay, and these are the nodes in the output layer, and here they are maybe in hexagon structure or maybe just in mesh structure. Here I have shown that they are mesh structure. And how many total number of nodes? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7. So 7 into 9, 60. 7 nodes. Okay, but generally we take of order, say m square, that is m number of columns and m number of rows. Okay, now what is the dimension of the input here? The dimension of the input is 1 to n. Here we have assumed the input is n dimensional. So what is dimension? For example, I am the input. So I have been explained or defined by my, say, height, maybe the name, maybe my age, maybe my expertise, maybe my department. So all these are my features, right? So say there are so many people, say 500 people, so 500 data points, and for each of the data points there are n such features. Okay, so here we have shown this x is one such data point, and the number of features, that is dimension, is n. Okay, so all these input, this is a single input, so there are so many inputs uh, that will be mapped to this number of nodes. Okay, so this is, there is only one layer called output layer, and these are the main nodes in the sum. That's why we call it neuron. Okay, neuron in the sum means actually the output nodes, but these nodes are not neuron. These are just to show that an input is represented by these nodes. So how many nodes will be there in the input layer? The number of features of the sample. Now you see that all the nodes here actually connected to the inputs. Connected to the inputs mean how many features? N features. So all nodes are connected to all these nodes. That is the neuron. Each and every neuron is connected to all the features to a corresponding element or data or sample. Okay. Now it shows that there are m square such node in the output space. Here we have used also a mesh lattice. Okay, and it contains m number of rows and m number of columns. So you see 1, 2, 3, 4 m plus 1, m plus 2, in this 2m, and in this way it is m square. Okay, so each and every neuron in the output space is connected to the input. In this case, input is x, and the features are x1, x2, x3, xn. Number of features n. So for each and every point, how many such connection? N such connections. Okay, and these, for example, this node, say we are considering this neuron, right? So you see here one connection for one feature, another connection for this feature. So n such connections are there, and these connections actually will be represented by a weight. Okay, so what are these weight? 1 m, that is from one feature, first feature to m, second feature to m, and nth feature to m. So there are such a neuron or a node in the output layer is specified by n number of weights. Okay. Similarly, here you see for another, I have shown only two such connection. Otherwise, it will be very dirty. That's why there are such n connections. For each and every node of m square node, they are connected to all these nodes. Now, another point is neighborhood of a neuron. Now, here you see, this is one-dimensional output layer. Now, each and every node of the output layer is connected to each other. That is, this is connected to this node, also to this node, also to this node, also to this node. You see, this is connected via this is connected via this, and so all the neurons are also connected to each other. Theoretically, I will consider that is this connection is not always very strong. They who are close to a particular neuron, the connection will be more strong than those who are far away. This is for a single dimension or one-dimensional layer, output layer, and it shows two-dimensional. Oh, sorry. it shows two-dimensional. Okay. And in this case, you see each node is connected to all the nodes. But here, the link which is shown only to its neighbor, closest neighbor. But that does not mean the connection from this to this is not there. The connection is there also like this, but it is not shown to avoid the complication or the such that it we can see it simply, right? Now, for each node, there is a neighbor. Okay. Now, say in the one dimension, this is a node in the output layer. So, what is their closest neighbor? So, this is one neighbor and this is one neighbor. Then the question is, these are not the neighbors. Of course, these are also neighbor. But in this case, their neighborhood relationship is less than the neighborhood relationship of I with these two. Similarly, for two dimension, here you see, if we consider the node I, then these are the nearest neighbor 1, 2, 3, 4, 5, 6, 7, 8. These are also neighbors, but in this case, the connection will be weak. Actually, we will make the connection weak. That you will see through the algorithm. That is the very sweet property of song. So these actually color, red or orange color is shown to show the closest neighbor of a particular neuron. Okay.
Ma'am.
Yes.
Yes.
Hello.
Yes, ma'am.
Yes.
Ma'am. In the in ma'am.
Okay, continue. Take time.
Yes, ma'am. Ma'am, in a picture, you have told that one ball is
one node in the output
M,
layer.
and after that, this is 2m, 3m, and then m square. Ma'am, and x1, x2, xn are the features. Ma'am, then ma'am, the data is n dimensional.
Right.
That's and
yes.
each and every coordinate is suggesting one feature.
Yes.
And ma'am, why this is
we don't call it coordinate. Coordinate actually in cluster I have called coordinate because it represents only two-dimensional. But in this case, it is when it is more than that. For example, this. Okay. So it is n-dimensional input. So for a particular element, there are such n values which defines that particular element or data.
Okay, ma'am. Ma'am, and why this is denoted as m2m and then m squared? What this is symbolizing, ma'am? The output space.
You see, actually in output, this is the output nodes in the output layer, and actually these neurons will actually represent all the input samples. That is, you see, say there are 500 such samples. So there is a space of n-dimensional space, and in that n-dimensional space, which we cannot show in this slide, there are such, say, 100 or 500 or maybe 300, maybe more than that, samples are there in an n-dimensional space that we can't visualize, right? But those samples from input space will be mapped to these neurons or nodes, which we can visualize. And these nodes actually, they will be change their position, and their position actually will be similar to their distribution to the input space. That you will, I think, we will understand later. Just we have started the sum, what is its architecture. So in this case, here I have considered is as a square, that is m square, that is m nodes in row wise and m nodes in column wise, but it may not be m square, it may be, say, L by m. So L number in the rows and m number in the column, just by a matrix. So it is equivalent to a square matrix. May not be square, it may be, say, m by k or L by m, like that. Okay. just for discussion, we have considered it is a square grid.
Okay, ma'am.
Any more question?
No, ma'am. Thank you.
Now this is actually shows the neighbor. Now you see how this neighborhood relationship is represented. Actually, neighborhood relationship is represented by this function, and this type of function actually, it actually may be the Gaussian function. You know the probability distribution, normal distribution, right? So this is a Gaussian function. What is the special characteristic of Gaussian function is that it is not just proportional. Okay, say this is the, these points represent the a node. Okay, and we want to find the neighbor of this node. Now this shows the distance from the node I. Okay, and then this vertical axis actually shows the relationship. Now if this is the I node and say these are the different nodes, okay, now say this is a node K. So this represents the distance between neuron I and neuron K. Okay. So K is a neighbor of the neuron I. Okay. And how much close they are, or neighborhood relationship, how close it is, that will be represented this the vertical line. And you see, less the distance, more is the relationship. And ultimately, the question is, I have told all the neurons are connected and all the neurons are the neighbors of all other neurons, theoretically, right? But realistic, in reality, real scenario, you see, if a neuron is more than this distance, that ultimately we can ignore the neighboring relationship. Is it clear now? So you see this type of function, say this phi I k, it represents the how much strong is the neighborhood relation between I and k, where I is the neuron from whose neighbor we are considering, and k is considered a neighbor of neuron I. So this center point is called the I, and all these points represents its neighbor. And their relationship is actually, you see, exponentially, it is decreasing. That is, after a particular distance, we can say all these K neurons are not actually the neighbor of this neuron. And this is actually, that's why generally we use the Gaussian function to represent this neighborhood relationship. Okay. Now I would like to show in sum what does it represent, neighborhood of neuron. Now this is actually one input. Actually I can show the input by this task bar. Let us take it here. Right. Okay. Now here x1, x2, x3, actually they say there are just, we have considered three features are there. So in the input there are three nodes, and in the output we have considered a mesh, right, having 1 2 3 4, 1 2 3 4. So 4 square, here m is equal to 4. So 4 square, that is 16 nodes are there in the output layer, and it is in a mesh structure. Now, these are the neurons, and say just one particular input is given for learning. Actually, the input will be given one by one, and accordingly, the weights, rather the position of the neurons will be updated. Okay. So in this case, x1, x2, x3 are the features. And what does it represents? It represents the weights of this neuron. So these weights are nothing but its connection. It is connected to the input. This is a single input by this connection. Similarly, all the nodes are also connected to this neuron. Okay, to this input. So you see, this is also connected by this way. So you see, a node is represented by a set of weights. How many weights? The number of dimension of the input. Okay. This node is also connected. This node is also connected. All the nodes are connected, but I have shown only the first four. Now, actually, what it happens? X1, X2, X3 are the features. And in node, there are, say, for this node, this is omega 11, omega 12, omega 13. So omega 11, omega 12, omega 13, you can consider as the property or feature of this node, neuron. So what does song do? The distance between this node and this sample is computed. The distance between this node from the sample is computed. So actually, the distance of all these nodes from the given sample is computed. And that node is the winner who is the closest to the input. And in this case, we have assumed, say, this node is the closest. That is the distance between this node and the input, and the distance between the input, and the distance between this and the input. Among all the distances, the distance from this node to the sample is least. So for this particular sample, it is the winner. Now you see the input will be mapped to the output, and this represents the output space, right? And in the output space, actually, these nodes ultimately will represent the samples. So for this sample, currently, this neuron will be used to map this input. And accordingly, actually, we will shift it in such a way that this will be more close to the input. Now the fact is, this is the winner, but the fact is there are neighbors also. And theoretically, all are the neighbors. But you see, as it is the winner, so it will try to represent this input. So it will be shifted more close to this input. And as they are the neighbor, closest neighbor, they will also be shifted, but less than this winner. And they will be shifted very less. And ultimately, who is in the furthest of this winner, that is negligible, and we can discard it, as we have defined the neighborhood regression by the Gaussian function. Have you got it? So when a sample is given, we find the winner, and we change the weight of the winner such that it moves to the sample, and all other will also be moved, but less. How much less? It represents according to its neighborhood relationship with the owner or winner, right? So in this way, we will give all the samples one by one, and the weights of all the nodes will be adjusted or updated. That is actually learning in song. Okay, now you see this. Say for a particular, say this is the a sample and n dimensions. However, we have shown only 2 dimensions. Okay, and this is the grid output layer, and actually this shows the relation with the neighbor. Say for this input, this is the winner. Okay, so winner will be shifted to the input in the outer space. So actually, this will try for current iteration. This will represent the input. So it will be shifted to the in such a way that will be more close to the input, and its neighbor also will be shifted. But how much, that will be done according to their distance from the winner. Okay, and that's why you say this is the a node in the output layer. This is not the input feature, right? Though blue, this is a node in the output layer, say jth node. So for jth node, you see how many weights are there: omega j1, omega j2, omega j3, omega jn, because they are n-dimensional input space. So this minus this, okay, that will represent the distance of jth node from this. Okay, and this, for the winner, this distance will be made more, will be decreased, that is shifted to the neuron. Is it clear? Now this is the learning algorithm which I have shown, that is done here. So first, for node, though I have represented in so nicely in a systematic manner, but just like centroid of the cluster, okay, so they are randomly taken. That is, their weights we assign randomly. And in this case, we have considered it is a square grid, that is n square number of nodes are there in the output space. Now we will choose the sample one by one. Okay, and we have considered one input sample x, and this is the x, and this is the I is the a neuron, ith neuron in the output layer. So for all I, we will compute the distance, and this is the Euclidean distance. You know how to compute it. So from among all I, we will choose one which is the closest, and say this is the kth node. Among all I, kth node is the closest. So node k is the winner, right? Now for node k, as well the neighbor of k, the weight will be changed. Okay, so for all I, the new I will be old, new weight will be old weight plus this change. Now if it is as it is like Gaussian, right, neighborhood function, you see it is multiplied by the distance. So more the distance, less will be this change, and eta is the learning rate. We take the eta. I am not going to the learning rate. If you know neural networks, MLP, you know what is learning rate. If learning rate is less, then the learning will take much time. If it is learning rate is high, the learning will be faster. But that does not mean that always we will use eta a large value. Then there may be many problem like stacking minima like that. So choice of the value of eta is also a significant or important factor. I am not going to this. So in this way, we will take the sample one by one, and the nodes will be weights of the neurons will be changed. And what is the principle, that winner will be shifted to the input, and the neighbors are also will be shifted, and of course this change of weights are more to the winner, and for neighbors it will be less according to the distance of the neighbor. In this way, you will see at a particular iteration, the nodes are not being changed. Okay, so then we can conclude that the sum has been conversed. Then the position of the nodes are actually represent the distribution of the input. And there may be, for example, there may be thousands of samples in the input space or having n features, but you see here only 2 dimension in the output space having, say, only m square, say m is equal to 15, or sometimes we take it each more, but it is in 2 dimension, and the distribution of these nodes will be similar to the distribution in the input, because it maintain the topology of the input space. The topology of the input space will be maintained in the output space. So the position ultimately of the nodes will preserve the topology of the input. That is the neighbor, those points in the neighbor, samples in the neighbor which are close, that will be shifted to those nodes in the output layer which are close to each other. So we can visualize so large data set through a small number of nodes. Okay, and we can then conclude so many things, the relationship that I will show the later. Hello, Dr. Shankar, how much time I can take?
Yes, sir. Yes, madam. You can continue, madam. Up to 15 minutes and 20 minutes, no problem.
Okay. Now it shows, say, this is now the current position of the grids. That is actually the intersection of this intersection represent the node, right? And this is actually it represents the actual input space. Okay. Now you see, say this sample is given white. This sample is given. Now for this sample, this node, hello, can you see my, can you see my cursor?
Yes, ma'am. Adaptation of SOM.
So you see this node is the closest to this sample. So when it will be updated, it will be more close to this node because this is the winner. And you see the neighbor of the winner is also being shifted. It is just like an elastic grid. It is also being shifted to this point. But the amount of this shifting is much more for the winner and much less from the winner for the neighbors, and much less negligible for which are far away from the winner. Okay, so in this way, when you will give the input sample one by one, then ultimately you will see this will be the structure or the positions of the nodes, that is the neurons. And if we consider these neurons, and how many neurons you see, 1, 2, 3, 4, 5, 6, 7, in this way, all the intersection, these nodes just show us the whole input space and where resolution is much better. So from this visualization, we can conclude so many things, the interrelationship between the samples, and I will show some of it. Okay. Now, the same thing I have tried to show you. This is the winner, right? And you see one, and this is the sample xj. Okay. And how many? This is, so I have represented it here. Okay, so this is the winner, and say this is the sample is in different space, right? But just we have represented by this point as the as the sample, and this is the winner. So ultimately you see the winner is being shifted to xj, and the neighbors, you see these neighbors, 5 neighbors. Okay, 1, 2, 3, 4, 5. 5 neighbor has also been shifted, but this shifting is much less, right, than this shifting. Is it clear? So the same thing which I have tried to represent in many ways, actually. So this is the single input, and this is the winner. So winner are now being shifted to some other positions such that the distance become less. That is, the weights are being changed. Weights are being changed means the position of the node is being changed. Okay. So in this way, now I would like to go its useful property. One is the topological ordering, and actually it means that the similar input sample, where similarity is defined in terms of the input variables. Actually here input variables means the features, age, maybe sex, maybe height, maybe weight. Say this is a person, each sample is corresponding represent a person, and a person is defined by his or her age, sex, height, and weight. Okay, so in that case we will see that all 55-year-old females that are approximately 1.6 meter in height, they will be mapped to nodes in the same area. That is, all those input samples will be ultimately mapped to say 2, 3, or 4, 5 nodes of the SOM. Okay, and this property, topological ordering property, actually we take help of it rather by this property, useful property of SOM. Actually, clustering is done by SOM. That I will give some example. Now, what are the other property? Approximation of the input space, because the input space is being mapped, the whole input space is being mapped to the grid. So you see here, actually this is the input sample or input space, and this is the output space. Initially it was the output space. Ultimately this output space, you see, the cover the whole input space. So we can just take the grids to represent the all the samples. This is called approximation of input space. And density matching, you will see, if there are so many in a space, if the occurrence of input is much, the probability of occurrence is much more high, then of course the corresponding domain in the output space will be large. Okay, so the density matching is also maintained by SOM. And feature selection, this is very important for SOM. Feature selections means mapping. So a high dimensional data is being mapped to a low dimensional data. This is called feature map. This property of feature map is used by many applications. Now, this is the example of input space approximation. Here, all the red colored dots are representing the input samples. You see how many input samples are there. And only these mesh represent the grids. And how many grids or nodes or neurons are there? 1, 2, 3, 4, like this. So you see, ultimately, this shows the positions of the nodes, which actually represents the whole input space. So we can just discard the input space, and we only consider these grids which represent the input space. This is called the approximation. And you see, already I have mentioned that the output layer may be one dimensional, maybe two dimensional, maybe other dimensional. So if the input is two dimensional, then how it will be mapped to one dimension? That is shown here. So this is the input space triangular, and these are the samples. But ultimately, you see, when it has been learned by SOM, you see the input space has been covered by the one dimensional SOM. This actually represents the grid. Small circle represents the grids. Okay, but the blank space is not the blank, right? This is actually the a large number of samples. Large number of samples are there in the input space which are not shown, but only the grids are, or the neurons are given here. This is the initial random position, and ultimately they has been, you see, they has been arranged in such a way that this whole grids represent the input space. So you see, even if the input space is two-dimensional, then also SOM is capable to map it to one dimension. Now you see here two different data sets are there, and here the input samples are represented by red points, and here the input samples are represented by black points. And you saw that how the mixed structure is formed such that it actually approximates the whole input space. And this is also same, and you see the density of the grid, you see much more here, though the number is less, which is which shows the similarity between the input space and output space. And in this case, you see density is also best. You can see more number of neurons are there, where the more number of samples. And also you see how you can see it is more or less a clustering. So you can consider this is one cluster, you can consider this is one cluster. So clustering can also be done by saw. And this is another, you see the two-dimensional input space is being mapped to two-dimensional output space by saw. So there are so many samples which is not shown, and these are only the grids and random position, and ultimately you see how they are arranged. As it is, we are considering that all these are very uniform. So the grids are also, you see, in this case, are very uniform. And these are shown by the density matching. The red points are the samples, and more samples are there, and obviously more number of neurons are there. Now let us go for clustering. I am just already I have told that topology preserving characteristics of some is mainly responsible for this clustering. Now just you see here, the already I have partially explained it. Okay, say x1 is one input sample and x2 is another input sample, and for x1 O12, okay, is the winner, and for x2 O11 is the winner. Okay, now let us consider x1 input, and what are the features of x1, x11, x12, x13. That is here for simplicity we have considered only three features. Okay, now these input is connected to all the nodes, but here we have only considered this and say this is the winner. So winner will be the weight, this weight will be changed, as well as its neighbor will also be changed. Of course, the change of these weights will be much more than the change of the weights of these nodes. Okay. Now say x another how it comes. This is just, I think, by mistake, x13 is here. Today I have done this mistake. Now another point, x2 is given, right? So for x1, you see x12, this is the winner, right? For x2, say x011, that is this 011, say this is the winner. Because x1 and x2 is very close to each other, we have assumed. So in this case, of course, the winner also will be close to each other. So this is the winner. Now for this winner, you see, this is the neighbors. Now you see, this is the neighbor. This neighbor is the winner of the previous sample. Okay, and this is the neighbor of this winner as well as this winner. So you see, for the similar similar sample x1 and x2, the corresponding grids also similar to very close to each other, and that is responsible for clustering. Now just to show you that these samples, orange color is used to show the input data samples, and the black points are shows the black points show the neurons, and the connection is shown is nothing but the blue lines. Okay, is shown by the blue lines. Now you see, using SOM, you see how many clusters are there actually in the input data. 1, 2, 3, 5. And you see, using SOM, we can also see that clusters have been formed, but not very perfect. Why? Because you see there are some neurons are there which actually are in between the clusters. Okay, but if somehow we can avoid these 4 neurons, or you can shift it to this cluster or this cluster like that, then it could be a good clustering. And that's why many people have used the SOM as the initial phase of clustering, and they have modified to make the clustering tune in a very more or better way. For example, here you see, just I have shown this is done by some and this is done by some, but in a different way. There are some modified some. You will see the paper, most probably it is in 2010 or 11. Okay, they have so many works are there in the literature who have used some for clustering. However, they have done some tuning or making the clusters in a better way. They have done some modification. And this is another example actually. Actually, some you can now guess that if the samples are very contiguous and continuous, very dense, then actually some will form the cluster very well. But if it is discrete, then there may be some this type of problem may comes due to some nodes, right? Output layer, nodes in the output layer. Now, in this case, these are all the samples very close to each other, contiguous, and they are in represented in these 8 colors. Okay. Now, if we use some for learning this, ultimately you see the 8 colors have represented just like 8 clusters. 1 and how many clusters? 1, 2, 3, 4, 5, 6, 7, 8, which belong to this class. And I have given for example, this is shows the learning. This is the initial, and then it learns to 8 clusters. And if you go to this website, you will get this work. I have just copied from that today to show you. And there are so many metrics, for example, soft heat map, U matrix, to show the relationship among the features. Okay, and some are an unsupervised data visualization technique. I have shown that is high dimensional data can be visualized very well through the 2-dimensional output layer of the SOM. And heat map is the technique, okay, by which we can use it for different observation. We can observe it, and just you see that these data have used here used for the area in Ireland, I think, and this is around Dublin, and this is the heat map, 2 heat map, but the data set is 1, and it shows that this is the heat map on unemployment percentage, and this is the heat map of average educational level. And from this you see unemployed is more when education level is less. So if there are, for example, 5 features, we can do 5 heat maps, and from these heat maps we can do many conclusions. For example, say customer, we can segment the customers and we can find out which customers prefer which items for data mining purpose. Because in big data you need the clustering. Clustering is very important for big data, and in that case some can be used by this. And this is nothing but the ratios have been expressed in different way. So U matrix, heat map, these are the from the same learning of the song, but we can interpret it in many ways according to our requirement. In real life application, we can collect real life data, and from that we can conclude which will be beneficial for the industry or maybe for the society. Okay, and here you see this is the average age. The same data you see 1, 2, 3, 4, 5, 6. 6 features we have used here. These features, and from this you will see who are unemployed. Then of course number of cars is very less or no car, and for unemployment percentage you will see they may be, most of them may be unmarried, and educational level is less, like that. Okay, So this is just to show you, to encourage you that SOM can be used for so many purposes in real life application. So I am not going to the conclusion to discuss, because already we have discussed a lot. So I will send my PPT to the organizer, and you can collect it. Thank you for your patience.
Thank
I
you, madam.
thought I will take
There
only
are,
1.5 hour, but I have.
no.
Thank you.
Is there any question?
Yeah, I am ready.
Is there any question, participant?
Ma'am,
Yeah,
thank you for your nice talk.
thank you.
Ma'am, I have a question about the output space and the input
Yes,
space.
yes.
Ma'am, when I'm finding the distance from the each feature to the output space,
Uh,
when n equal to greater than 2 and the output space is 2 or 3 dimensional, then how can I find the uh, distance between them? As there is a dimensional
oh, just a minute, just a minute. You see, n is the number of features
yes,
for one sample. So if there's 100 sample, for each of the 100 sample, there are n features. Okay,
yes,
and for each node in the output layer, you will see there are n such weights, right? These weights actually represent a neuron. So n weights is equivalent to a neuron, and n features is equivalent to a sample. So if we take the difference between, that is the distance between this, then that will be the distance.
okay, ma'am.
Dimension of the output is 2 dimension, but for each node or neuron in the output layer, there are such n such weights. When you will compute the weight, then distance, then for each and every neuron, you have to compute the distance from the sample. So there are n such component in the sample, or n such component for each neuron. So it is easy to compute the difference, right?
Yes, ma'am. I got the idea, ma'am. Thank you, ma'am.
Yeah, actually, I have, it is not so easy to visualize, frankly speaking. Still now, there are so many things I have to understand it in more detail. So this is just the introduction to give you the idea of what we can do with the SOM, what are the useful properties of SOM, what is the working principle behind SOM, and what is the difference between the working principle of SOM and working principle of cluster, how the cluster is being formed by SOM, whether the result is same, however how it is done by other clustering algorithm, right? There will be so many works you will see in the literature that by some they are actually trying to do hierarchical clustering, that also are also trying to give the good results. Okay, so hello my participant, students and faculty members. If you are willing to work on this, or if you want to use the SOM for your purpose, if it matches with your work, then I think you will study it more and you will understand in or visualize it much better way. And really, it is difficult to visualize the mapping from an n-dimensional input space to 2-dimensional input space. Frankly speaking, I think it will be clear with time if you
I
study.
think, I'm sorry to interrupt, Shankar sir. I think there is a question from Shankar Ashok Nath. So
Okay.
will we take the question?
Sure, we can
Or
take. Sure.
yeah. So the question is there any possibility that there may be more than one winner? If yes, then how to solve the problem?
You tell me, is it possible? If the distance is same, that means actually they are same. Neurons are same. Two different neuron means they are in different position, right? Have you got it? So if the grid are different position, then that is the connections are different, then there should not be any such tie, right? As I understand. If we consider n square grid, then it will be always n square. Even if it say one grid is after shifting, it matches with other grid, then actually the two distance, if it is same, then you will take only any one of them. But ultimately, when you will visualize, then you will see one grid will be less. But I think I have not such not yet got any such example, because different grids maybe what you are guessing that by shifting or changing the weight, maybe the weights of two grids will be the same, right? But I think it is rare, because their change is also proportional to their current position. So always the number of grids in the output layer will be maintained.
Okay, madam.
Madam,
here is another question.
Okay.
Suppose the members are dynamic and moving, then how do you cluster them?
That's a different procedure, right? That's a totally different procedure. Dynamic clustering, which is done in sensor network, wireless sensor network.
Okay, madam.
That will take time. I have actually now I am doing work on wireless sensor network with one of my colleagues. We are jointly supervising one scholar. So, and in that case, the dynamic clustering is required, because cluster head of the wireless sensor will be, then we need to change it. But we have not done it with so. I don't have enough expertise to answer it. Thank you.
Okay, thank you, madam, for giving us a nice presentation. I think all the participants are enriched.
Okay.
Thank you, madam.
I am requesting that you will get my number and the email address in our website, in IT's website. Thank you all. I will send.
Excellent presentation, madam. Excellent presentation. Really, we liked it.
It's my pleasure. And if even any one student can understand and utilize it, that is my success actually. Hello, Dr. Shankar. I will send you my slides. Huh?
Yes, madam. Yes, madam.
Okay.
I shared the materials to the participants.
Okay.
Thank you, madam.
Thank you.
Thank
Goodbye.
you.
Good
Thank you.
Then I am leaving, huh?
Yes, madam. Yes, madam.
Dear participants, we will be back tomorrow at 3 o'clock.
Feedback form? Prem, feedback form, is that given or that?
Yes, sir, we have provided.
Oh, okay, sorry, I did not notice that.